Hi, and welcome to Trial by Air. I'm Ryan, and my co-host Rhythm and I are aerospace engineers. We want to share our knowledge and experiences in the field of aerospace engineering, but more importantly, we want to bring to you the knowledge and experience of experts in their field. We started Trial by Air to learn more about applied and theoretical engineering, and hopefully, when you come along with us, we can do a good enough job of explaining it so you can learn something too. On November 21st, 1783, the Montgolfier brothers' hot air balloon carried passengers Pilatre de Rosier and Marquis de Orleans. The balloon rose to 3,000 feet above Paris and traveled around 5.5 miles. Later that year, on December 1st, Jacques Charles and Nicolas Louis Robert launched a hydrogen balloon that ascended to an altitude of 1,800 feet and covered a distance of 22 miles.
Before the advent of heavier-than-air vehicles, humans used lighter-than-air vehicles to fly. Lighter-than-air is a bit of a misnomer because the vehicles are actually not lighter than air. They're less dense than air. A more accurate name for these vehicles is aerostats. Aerostats is derived from aerostatics, a principle used to make these vehicles fly. Aerostats included balloons, blimps, dirigibles, and hybrid airships. All of these mostly rely on the principle of buoyancy for lift. This is achieved by using a lifting gas. But before we jump into lifting gases, let's dive into the fundamental principle of buoyancy. Using a free body diagram, let's walk through the force of buoyancy. Let's place our object in a fluid. We can think of fluids as either a liquid or a gas. So in our case, we will use either water or air. Our object will naturally displace the volume of the fluid that is equal to the volume of the object that is submerged in the fluid. This is similar to when we enter a bathtub and the water level rises as we submerge ourselves. A better example of this is when as kids we would go to use graduated cylinders to measure the volume of irregularly shaped rocks by measuring how much the water level rises. This is Archimedes' principle. All objects within a fluid do this: a balloon filled with helium, a person on Earth, or even an aircraft flying through the atmosphere. In each of these cases, the volume of the object is displacing the volume of the fluid that is surrounding it. Buoyancy is categorized as a body force, a force that depends on the volumetric geometry of an object. This body force is one of two forces that are acting on not only just aerostats but on everything in the atmosphere. Buoyancy is even acting on the fuselage of an aircraft. However, more often than not in initial analyses, body forces are neglected. An important detail to note is that the fluid in which the object is suspended in is not in motion. Buoyancy concerns itself with non-moving fluid motion or fluid static. We can define buoyancy as follows. Fb equals rho times g times v. The buoyancy force is equal to the gravitational force times the density of the fluid, which again changes as you change in altitude and temperature, times the volume of the object. This is the cross-sectional area of a uniform object times its height. The density times the volume gives us a mass, and that times the gravitational acceleration gives us a force. This force experienced by the body is equal to the weight of the volume of the displaced fluid. This principle is what's used for dive and ascent of submarines, which changes the buoyancy force by changing the density of the vehicle via taking on or removing water from the ballast tanks. Let us know in the comments below if you want us to dive deeper into the mathematics and the derivation behind the buoyancy force.
Lifting gases are gases that are less dense than the surrounding air, and they're used in order to generate the buoyancy force required to lift the vehicle. Hot air was the first lifting gas used for aerostats. Hot air leverages the ideal gas law, as you remember from chemistry, as pressure times volume is equal to the number of moles times the gas constant times the temperature. If we keep the pressure constant and we increase the temperature of the gas will expand to fill a larger volume, thus making the gas less dense than the surrounding air. This is used to generate the buoyancy force required to lift the vehicle. The disadvantage of using hot air as a lifting gas is the need to carry the fuel to heat the gas, because if you do not keep heating the gas, the air will cool down again and contract to the same volume it occupied before, making it as dense as the air surrounding it, meaning no buoyancy is generated. The second and most common lifting gas is hydrogen. Hydrogen is the lightest gas, making it the most efficient lifting gas. However, the hydrogen molecule is extremely small and can easily diffuse through most materials that are used in constructing airbags. Hydrogen is also extremely flammable, making it risky, as seen in the Hindenburg accident, where static electricity built up on the vehicle and discharged when it docked, causing the entire vehicle to catch on fire. The most common lifting gas used today is helium, and the advantage of helium over hydrogen is that it's the second lightest gas, so the second most efficient, and it is inert. The disadvantage of using helium is that helium is non-renewable and will become more expensive over time as most of the helium gets consumed. There are many other theoretical lifting gases with potential for use, but only hot air, hydrogen, and helium have been used historically, sometimes solely and sometimes paired with other lifting gases. There are many different types of aerostats. These include balloons, dirigibles, and hybrid airships. Balloons can be broken down into two further categories, such as tethered balloons and steerable balloons. These names kind of speak to themselves about what they do. In dirigibles, which means a steerable vehicle, it takes the shape of an enveloped craft, kind of elongated like a cigar, with a gondola underneath with power generated by propellers attached to the gondola or to the envelope. Now, in dirigibles, there are three different types of dirigibles, one of them being rigid, semi-rigid, and non-rigid. The envelope is the part of the vehicle that contains the lifting gas, and in rigid or Zeppelin airships, that shape of the envelope is dictated by a rigid structure underneath, hence a rigid dirigible. In a semi-rigid, part of the shape of the envelope is relied upon the structure or the gas bags. In a non-rigid or blimp, the shape of the envelope is entirely dependent upon the gas bags. Hybrid airships are very similar to semi-rigid or rigid airships in that they rely on a structure to give some shape to the vehicle. The vehicle relies on both buoyancy and lift generated from the shape of the vehicle in order to achieve flight. Aerostats competed with heavier-than-air vehicles in the early history of aviation and were the only aircraft capable of long-range endurance and long-range flights at the time. Balloons were used for scientific study of the atmosphere and for cartography. Balloons are still used in this capacity today as weather balloons that can record the atmospheric conditions from the ground level up to high altitude. Balloons can reach higher altitudes than most aircraft at the fraction of the cost and can be at these higher altitudes longer than any other aircraft, rocket, or projectile. For this reason, many high-altitude research missions use balloons, such as Project Manhigh. Balloons have been used as atmospheric satellites that can provide telecommunication, surveillance, meteorological data, and real-time monitoring of a region for an extended period of time without the cost of a satellite. For example, Google's Project Loon uses high-altitude balloons for high-speed internet. In the United States, blimps are a common sight at outdoor sporting events, as the blimps are able to provide aerial coverage for extended periods of time at relatively slow speeds with minimal fuel burned. The predominant military application of balloons and other aerostats has not changed from its initial use as an observation platform. With the design of hybrid airships, aerostats have been considered for use as cargo transports, but have yet to materialize beyond the point of a prototype stage, the most famous being, and the most recent being, the Airlander 10.
For more resources, check out the Fundamental of Aerodynamics 6th edition by Anderson. It has one short but extremely detailed section about fluid statics.
And be sure to also check out the Fundamentals of Aircraft and Airship Design, Volume 2 by Nikolai and Kerkner. It covers rigid airship, blimp, hybrid, and balloon design.
Well, folks, I hope you enjoyed today's episode. Be sure to ask us any questions you may have thought of in the comments below, and we'll make sure to address those in the next episode. On behalf of my co-host Ryan, we'd like to thank you for listening today, and we hope to see everyone again in next week's episode. Thank you, and goodbye.